Welcome back, Dr. Tullis here. We are moving on to the next section looking at the water ionization constant, Kw, and using the pH concept. Because we generally use aqueous solutions of acids and bases, and because the acid-base reactions in your body occur in your aqueous interior, we want to consider the behavior of water in terms of chemical equilibria. To a very, very small extent does water ionize to conduct electricity. The equilibrium expression, or our Kw, is the auto-ionization constant for water, is as follows. Here's our water as a reactant, and we're saying that it is in equilibrium with H3O plus ions and OH minus ions. So here's our reactants. Our reactants is if I have two waters, so H2O and H2O. And one of those waters will act as an acid and the other will act as a base. And if we have an acid, which is a proton donor, that would mean one hydrogen from this H2O would go to the other H2O, leaving me with an H3O plus. And then, because I would be losing one of those H's, then I would have an OH minus as a product. Water by itself, H2O, in liquid form cannot be written in an equilibrium expression. So our Kw, we look at our products, H3O plus times the concentration of the OH minus over reactants, but our reactants are both liquid waters, so over nothing. So our Kw is just the concentration of our hydronium ion times the concentration of the hydroxide ion. This water autoionization equilibrium is very reactant favored. In fact, pure water, only about 2 out of 1 billion water molecules are ionized at any instant. Electrical conductivity measurements of pure water show that our hydronium concentration equals the hydroxide concentration, which is equal to 1 times 10 to the negative 7. If I multiply 1 times 10 to the negative 7 times 1 times 10 to the negative 7th, I get 1 times 10 to the negative 14th, which is our water constant. Let's look at a practice problem. What are the hydroxide and the hydronium ion concentrations in a 0.0012 molar aqueous solution of NaOH? NaOH is a strong base. We know that NaOH, when combined in water, is going to completely split into Na plus ions and OH minus ions. We also know it's all a 1-to-1 ratio, so I'm going to have 0.0012 molar Na plus ions, 0.0012 molar OH ions. So I know the OH concentration, and I always know Kw. It's 1 times 10 to the negative 14th. So if I know that Kw is equal to our hydronium ion concentrations times the hydroxide ion concentrations, I know hydroxide, and I know Kw, then I can find the hydronium ion concentration. So I can say that my Kw is equal to hydronium times hydroxide. Divide both sides by that hydroxide to cancel it out. So 1 times 10 to the negative 14 divided by 0.0012 would give me my H3O plus of 8.3 times 10 to the negative 12 molar. Here's another one. What's the hydronium and hydroxide ion concentration in a 4 times 10 to the negative 3 molar HCl hydrochloric acid solution? Since we know the concentration of HCl and it's a strong acid, it will 100% ionize. So we know that it will ionize into H plus and Cl minus ions. Now, H plus ions and H3O plus ions are interchangeable. If you see H plus, it's the same as H3O plus. The only difference is leaving the water out of this. I'm showing the HCl is 100% dissociated into the H and the Cl because it's a strong acid. We could also show that we have a strong acid dissolving in water, and we know that the acid is a proton donor, so that H plus will donate to the H2O, leaving H3O plus and a chloride ion. So notice the difference here. I've got my chloride ion and I have H3O plus as opposed to H plus, but they are used interchangeably. So I took that hydronium ion concentration, and I always know Kw, so I divided both sides by that 4 times 10 to the negative 3. So 1 times 10 to the negative 14 divided by 4 times 10 to the negative 3 should give me a hydroxide concentration of 2.5 times 10 to the negative 12. The pH of a solution is defined as the negative log of the hydronium ion concentration. So in your calculator, you would take negative log and put in that H3O plus concentration. That will tell you the pH of the solution. We can also define the pOH of a solution as the negative log of the hydroxide ion concentration. Know that pH plus pOH is equal to 14, which is equal to the pKW. If I took the negative log of 1 times 10 to the negative 14th, I would get 14. We measure and use acids and bases over a very large concentration range. So the pH and the pOH are systems to keep track of those very large ranges. There's a lot of information in these 3 boxes. You already learned that the pH is the negative log of H plus concentration or H3O plus concentrations. Same thing. And the pOH is the negative log of the hydroxide ion concentration. In an acidic solution, so if it's acidic, that means that the pH is less than 7. That means that the hydronium ion concentration is going to be greater than the hydroxide ion concentration. We also know that the hydronium ion concentration will be greater than 1 times 10 to the negative 7th molarity. And the hydroxide ion will be less than 1 times 10 to the negative 7. In a basic solution, the hydroxide ion concentration will be greater than the hydronium ion concentration. And that hydroxide ion concentration will be greater than 1 times 10 to the negative 7th, which means the hydronium ion concentration, or the H plus concentration, will be less than 1 times 10 to the negative 7. In a basic solution, the pH will be greater than 7. In a neutral solution, the concentrations will be equal, and they will be 1 times 10 to the negative 7th. A neutral solution has a pH of 7. Knowing that the pH plus the pOH is equal to 14, can you tell me the pH of an acid with the pOH of 11? And find the pOH of a base that has a pH of 8? And the pH of an acid that has a pOH of 3. Since the pOH is 11, I did 14 minus 11 to get a pH of 3 for this first one. For the second one, I plugged in 8 for my pH, and so 14 minus 8 would give me a pOH of 6. And for the third one, I plugged in the pOH of 3, finding the pH of 11. Here's showing us a pH of 14 would mean that my hydronium ion concentration would be 1 times 10 to the negative 14th. So the negative log of 1 times 10 to the negative 14 would be 14. And it would be a very basic solution. Notice that this is a very small number, 1 times 10 to the negative 14, compared to 1 times 10 to the 0 would be 1. So a very, very, very small decimal compared to 1. The hydroxide ion concentration is much larger here, which is why it's basic. Compared to an acidic solution, notice that in this case it's flip-flopped. 1 times 10 to the 0 is 1, would give me a hydronium ion concentration greater than the hydroxide ion concentration, which would be acidic. And if it's neutral, then my concentrations are equal. So we said to get the pH, that we took the negative log of the concentration of the hydronium ion. So if I knew the concentration, I can find the pH. But what if I want to do the opposite? I want the concentration. I simply take 10 and raise it to the power of the negative pH. So if my pH was 3.2, I would do 10 raised to the negative 3.2 power, and my calculator would spit out 6.31 times 10 to the negative 4th molarity. You try it and see if you get the same answer. In a similar way, I can find the hydroxide ion concentration by doing the same thing, but I would use the pOH So 10 raised to the negative POH would give me my OH concentration. Once I know one of those concentrations, I can find the other. So if I know H3O plus, I can do my Kw, my 1 times 10 to the negative 14, and divide it by my hydronium ion concentration to get the hydroxide ion. Or if I knew the hydroxide concentration, I would do Kw divided by hydroxide to get the hydronium ion concentration. Pause the video here to try to find these two. I did the negative log of 1 times 10 to the negative 9 to get a pH of 9. And in this case, I did 10 raised to the negative 7.2 to get a hydronium ion concentration of 6.31 times 10 to the negative 8. I have several joining questions. We're going to pause the video after each one of these for you to try to solve it. Pause here. I was given the concentration of HNO3, which is a strong acid, so it 100% dissociates. That would be my H3O plus value. I need to find the OH minus value. So I plugged in Kw and my H3O plus and solved using algebra my OH to get 1.84 times 10 to the negative 11. Pause here. This would be a basic solution because if it was less than 7, it would be acidic. 7 is neutral. Any pH that is greater than 7 is basic. Pause here. We know that a pH of 4.5 would be acidic. Pause here. The negative log of the hydronium ion concentration would give me a pH of 8. Pause here. 10 raised to the negative pH gave me a concentration of 3.16 times 10 to the negative 5. Pause here. Because I was given the hydronium ion concentration, first I did the negative log of that hydronium ion concentration to get the pH. Then, to get the POH, I did 14 minus the pH to get that. You could have also put this right into Kw was equal to the hydronium ion concentration times the hydroxide ion concentration. You could have plugged this into there. We know that this is 1 times 10 to the negative 14. We could have solved for our hydroxide ion concentration and then taken the negative log of that. You would get the same exact answer. Pause here. I was given the concentration of NaOH, that's a strong base, so that OH concentration is 0.0015. You can leave it there or you can put it into scientific notation. In here they were all scientific notation, so I just moved my decimal to make it that way. I then plugged it into our Kw equation to solve for my hydronium ion concentration, which would be 6.7 times 10 to the negative 12. And then took the negative log of that to get a pH of 11.18. Pause here. I plugged this into my Kw equation to solve for hydroxide, and I got 1 times 10 to the negative 6. Pause here. Since I was given the hydroxide ion concentration, I did Kw divided by hydroxide to get the hydronium ion concentration. Pause. This one took a bit more work. I was given grams of NaOH. I needed to get to moles. Anytime, you should know that from Gen Chem 1. Anytime I have grams, let's get to moles. And once I know moles, I can divide it by liters to get concentration, and that would be concentration of my hydroxide ion. So I went grams to moles to get my moles of NaOH, divided it by 0.1 liters because 100 milliliters is 0.1 liters. So I got the concentration of my hydroxide. Then I plugged it into Kw is equal to hydronium times hydroxide concentrations to get my hydronium ion concentration of 7.47 times 10 to the negative 14. Here is a dilution problem. See if you can solve this. I was given M1 and V1. I was given V2, so I solved for M2. My concentration for my acid would be 0.1 molar. Once I know acid, I can find the hydroxide by using my Kw expression. And I got 1 times 10 to the negative 12.